Hi, I'm Eva Murphy from Electronic Engineering at IT Sligo, and this is my Leaving Cert Maths Grinds channel. I'll regularly add new videos for both higher and ordinary level maths, so make sure you subscribe below and click the bell icon to be notified of new videos. Let's have a look at this one. So this is a hard enough question in my opinion. It was the 2011 question and it was pre-project maths. So you won't see this one in your exam papers. It's kind of an older question. Not sure if it was the actual 2011 paper or a sample paper. Okay, so let me zoom in and just have a read. So a stand is being used to prop up a portable solar panel. This bad boy. It consists of a support that is hinged to the panel near the top and an adjustable strap joining the panel to the support near the bottom. So what it's telling you is that there's a support here that's holding up your panel and there's a strap here to tie them together. Okay, bit like whatever you want, a blackboard, a toy blackboard with a stand, anything like that that has a stand. By adjusting the length of the strap, the angle between the panel and the ground can be changed, which must be this one here, because I'm assuming that line there is my ground. Okay, so in other words, if you pull that strap tighter, then the panel is going to move in this way. And when that happens, your angle will get a little bit bigger. Okay, the dimensions are as follows. AB is 30. AD is equal to CB, so the two ends, is equal to 5. CF is equal to 22. EF is equal to 4. Okay, we want to find out how long the strap has to be in order to make the angle alpha between the panel and the ground equal to 60 degrees. Okay, we want to figure out how long the strap has to be in order to make that angle 60 degrees. Two diagrams are given below. One shows triangle CAF and the other shows triangle CDE. So CAF being that one. Okay. And the other triangle is CDE, which is this one here. Use the measurements given above to record on the two diagrams below the length of two of the sides in each triangle. So in other words, using this, see, can you fill in the dimensions on these two triangles? So give that a go there now. Right, so if we zoom in just a little bit and fill in some of these dimensions. AC. Okay, so I'm going to fill some in up here first. So it's telling me CB is 5. So this bit up here is 5. And this bit down here, DA, is also 5. Okay, and then AB in its entirety, so the whole lot, is 30. Okay, which must mean this bit in the middle is 20 because I'm taking these two 5s. If I subtract the 5 and the 5 off the 30, this bit here in the middle then must be 20. Okay, so let me come down to the diagram here. It goes from A all the way up to C. So it's 20 plus 5. So I make that one to be 25. CF then. CF was given in the question. It's 22. And this bit down here is 4. That bit is 22, the whole lot, which means the little bit is 18. Where did I get 18? 22 minus the 4, so C to E must be 18. Okay, so CF we're saying is 22, DC we're saying is 20, and CE we're saying is 18. Okay, I don't know anything about AF, I don't know anything about DE. Okay, So that's about as far as I can go with that one. Okay, the next part, part 2 of the question says taking alpha is 60, and don't worry about it if you call him A. Greek letters are used all over the place in maths, so call it whatever you want as long as you know what it's talking about. It doesn't matter what you're calling it. But it is alpha. It's taking alpha equal to 60 degrees. Find CFA. Okay, so where is CFA? So it's this little angle down here that I need to find. Okay, so non-right angle triangle is the first thing. So back I go to my log tables, and I'm non-right angled. So I'm down here. So I have the choice between the sine rule or the cosine rule. Okay, so if I go back to my question, I see that I have two sides. So it's lending itself towards the sine rule. Okay, I always put in lines that shows the side and the angle and the side across from it, the angle and the side across from it. So they are the pairs, and the sine rule works in pairs because the sine rule says that the side is the side that comes first. Yeah, A over the sine of A is equal to B over the sine of B, which is equal to C over the sine of C. So you can see all of these is the side and then the angle across from it, little b, big B, so the side and the angle across from it. So the sine rule works in pairs, which sorry guys, which is why I put in these arrows here, which links the sides with the angles across from them. Now, one thing to note about the sine rule is that you can flip it. It's the exact same thing in the sine rule to say sine A over A is equal to sine B over little b. Okay, and I'm only going to do the two sides here because we only ever use two at the one time. Okay, it is equal to sine C over C. Okay, so what did I do there? I flipped this side. Perfectly okay to do as long as I also flip this side. Why did I do that? Because what I need is an angle. So it's much easier then when the angle is on top. Okay, so whatever one you need, if it's a side you're calculating, then leave the sides on top. If it's the angle you're getting, as in our case, then take the version where the angle is on top. And then you fill in. Okay, so I would be sine of the angle 60 over the side across from it, which is 22, is equal to sine B, we can call it, or sine X, whatever you want to call it, or sine F over 25. Okay, I tend to cross multiply at this stage. You can cross multiply anytime the equals to is in the middle and you're dealing with fractions, because by cross multiplying, everything ends up being on the top and you no longer have fractions. So to cross multiply, it's this by this one being equal to this by this one. Okay, it doesn't really matter which one goes on the left and which one goes on the right. So 25 sine 60 is equal to 22 sine B. Okay, I'm going to divide across by 22 because I'm trying to solve for B. So I'm getting B as much on its own as I can. And then I'd like to put this into the calculator. Our angle here is in degrees, so just double check that your calculator is in degree mode because it could be in degrees or radians. So degrees, it'll have a little d at the top if it's in degree mode. And if it's not, you have to go into setup, so shift mode or shift menu setup, depending on what calculator you have, to change it to degrees. Okay. So make sure you can figure out how to do that. So I'm getting a 0.98412 is equal to sine B. Okay, the 2, I actually got 19777. I just rounded it up to 2. So 98. Okay, now we need to solve for an angle. And remember, when I was doing the theory bit here, I said that you'll use the sine inverse, cos inverse, tan inverse as well, anytime you need an angle. So anytime you're solving for an angle, you will end up using sine inverse, cos inverse, or tan inverse. Okay, they're the only times you really use it. So what am I doing? The opposite of sine is sine inverse. And I know that if I get the sine inverse of sine, because they're the opposite of each other, they cancel. Okay, so what am I left with on the right? I'm left then with just b the angle, which is what I want. Okay, now what I do to one side of an equation, I have to do to the other. So into your calculator, put sine inverse of 0.98412 or sine inverse of answer. And you'll see sine inverse sits behind sine on your calculator. And I am getting 79.775 degrees. And I'm just going back to see what kind of rounding do they want me to do on it. Correct to 1 decimal place. Do you see that up here? Okay, so I always put down the answer that I get in the calculator like that in case I make a mistake rounding. And I get 79.8 degrees for that part. Okay, so that's your answer to that part. Right, so let's move on. So all I've done here is literally just copied out that question again so that we have all the dimensions to let us continue on with it. So he was 25, 22, 20, 18, and now we've worked out that this angle down here is 79.8. Okay, hence find the angle ACF correct to 1 decimal place. So make sure you can read the maths language here. What angle are they looking at? Well, it's always the letter in the middle. Okay, so it's angle C in this case. So where do I get that from? Well, this is ACF. So you can see that it's the angle at C, no pun intended, up here is the one that they're talking about. So it's the letter in the middle. Okay, so how do we do that? Well, you know angles in a triangle add up to 180. So you take the 60 degrees that you know already and you add it to the 79.8 degrees and you get 139.8 degrees and you subtract that from 180. And you get 40.2 degrees, okay? So now we know this little one up here is 40.2 degrees. Okay. And then the last bit says, use triangle CDE to find DE, the length of the strap. Okay, why do we have to use the small triangle to get the length of the strap? Well, that's because the strap goes through the big triangle. So we're never really going to get the length of it in that particular diagram. Well, we're never going to get it from this diagram. This is a better one because the strap is the base of the triangle for this one. Okay, so a lot of students over the years, well, since 2011, struggle a little bit with this question in that you have to find the other side, which is DE, right? That's what you're looking for. It's not a right-angled triangle, okay? So you're using the sine rule or the cosine rule. Now you have 2 sides and you need a third side. So it'll always be the cosine rule in that case, because the cosine rule links a load of sides together. Okay, so I figured that out because I had 2 sides and I need the third side. Okay, so the cosine rule is a squared is equal to b squared plus c squared minus 2bc cos of the angle A. Now, if I'm going to find the side A, okay, little a, I'm going to call him little a. Okay, well, let me not do that just yet, and I'll explain that in a minute. Okay, if I'm going to find a side, then that implies that I should know an angle in this triangle. And as the diagram is drawn here now, it doesn't look like I have an angle. And this is where people struggled with this part of the question. In fact, you had to know that that angle C on the big one is the same one in the small one. Can you see that the top of that triangle is the same regardless of whether it's the big triangle you're looking at or the C? So in fact, I do know that that angle is 40.2 degrees. Okay, so we did have an angle. And if you spotted that in this question, then you were okay. If you didn't, then you could have been a bit goosed here in trying to solve it. The one thing you have to be careful of in the cosine rule is that whatever angle you're using, you have to call the side across from it little a. There's only one angle, so your angle is big A, so the side across has to be little a. And that is regardless of whether that's the side that you need the answer to or not. Okay, so I know that's my angle and it's the only angle I have, so this side has to be little a. And it doesn't matter after that then which is B and C. Now it does so happen that A is the side that I need in this question. I'm going to leave it as A. You could of course call it DE is equal to B squared plus C squared minus 2BC cos of 40.2 degrees. Okay, you can do that out all in parts, or it's just all numbers. You could just put it into the calculator all in one go. It kind of comes down to however you do your maths. Okay, I tend to make a fair old few mistakes in the time in these easier bits of maths, so I don't trust myself in many cases to put it in bits, so I put it in all in one go. Okay, but it depends on how your brain functions. We're all different, so whatever works for you. So that's what I'm getting for a squared. The side isn't called a squared, it's called a. So to go from square to square root, sorry, to go from a squared to a, I use square root. Why? Because squared and square root are the opposite of each other, just like sine and sine inverse were in the last one. So that I'm left with just a being equal to the square root of 174.067. So let me on my calculator go square root answer equals 13.193, and I'm going up here again to see how many decimal places. 1 decimal place, 19 is closer to 2.
If you are interested in technology or engineering, but are not doing higher level maths, why not consider our Level 7 in Electronic and Computer Engineering? This is a 3-year program that looks at the design and development of embedded electronic systems. These are the medical devices that keeps us healthy, the consumer devices that keeps us entertained, or the controlled systems that keeps us safe on the road. You can then progress on to the Level 8 in electronics and self-driving technologies, and from there to the Masters.
Check out the link below for more information.